Hello, my name is Allie, and today I'm here with Ross and Lauren, and we will be talking to you about relative acidity. If you need to know more about this section, it's section point 10 in chapter 19.
First, we will talk about electronegativity and how it affects relative acidity of a molecule. So as you can see here, I have a zoomed in picture of a periodic table which is focused on the more electronegative atoms in the periodic table. So as you can see from these arrows, the farther right and the higher up on the periodic table you go, the more electronegative the atom's going to be. So as one can expect, fluorine is going to be the most electronegative atom, which explains this part right here. The more electronegative the substituent, the stronger the acid. And the electronegativity leads to a stronger acid because it pulls electron density away, stabilizing the carboxylate ion. So now we will do an example of what I have just explained. So here on the left we have just a carboxylic acid, which has a pKa of 4.8. In the middle here we have a carboxylic acid with a chlorine attached to it, which has a pKa of 2.8. And then finally over here all the way to the right we have a carboxylic acid with a fluorine connected to it, which has a pKa of 2.6. So as one can see, the further right you go, the lower the pKa. And the stronger the acid, the lower the pKa it is going to have. So this is just one of the many examples that shows how the more electronegative an atom is, the stronger it will make the acid.
Amount of electronic withdrawing and donating groups. So as mentioned before in class, the stronger the acid, the stronger the conjugate base. So keep that in mind while you're watching the rest of this video. The more electron withdrawing groups, the lower the pKa. The lower the pKa, the stronger the carboxylic acid is. The more donating groups, the weaker the carboxylic acid, and the higher the pKa. Alright, so now let's look at some examples of withdrawing and donating groups affecting carboxylic acids. So in this first example, we'll look at withdrawing groups. So as you can see here, the first one has no chlorine atoms on it, but then the second one has one and the third one has two. So pause the video and see if you can determine which one is the most acidic and which one is the least acidic. As you probably guessed, the most acidic is the last one over here, which has two chlorine atoms on it. Then the middle one, of course, is going to be the one with one chlorine atom, and then the last one's going to be the one with no chlorine atoms. Now, the reason that this is because this one over here has two chlorine atoms which are withdrawing groups, and they are pulling the electron density towards them, making it more acidic. So I don't know the exact pKa's of all these, but what I would just do is I draw an arrow going this way, showing that it gets most acidic as it goes to the right. Now let's look at the second example, which are going to be donating groups. As you can see here, the first one has no groups on it, this one has one group on it, and then this one has two with donating groups on it. So again, pause the video and see if you can determine which one is the most acidic and which one is the least acidic. As you probably guessed, it's the exact opposite of the first one. It's going to go to the left instead to the right, and that's because there's these donating groups on here which are pushing the electron density back to the carboxylic acid, and then there's one here and none here, so that makes this more acidic than this one over here.
So when we're talking about the inductive effects in aliphatic carboxylic acids, another aspect that helps determine this is the proximity of the electron withdrawing group to the carboxylic acid. The closer the electron withdrawing group to the carboxylic acid, the stronger the acid becomes. This holds the same for the larger number of substituents and their proximity to the carboxylic acid. So the first example here shows the proximity of an electron withdrawing group to the carboxylic acid. As you can see here, the closer the electron withdrawing group becomes to the carboxylic acid, the stronger the acid becomes. So when it's way out here, it's only got a pKa of about 4.5, but one step closer, it's at 4.1, and when it's right here on the carbon next to the carboxylic acid, it's at 2.9, which is a huge increase in the acidity of the carboxylic acid. Now, for example 2, this shows the proximity of more substituents to the carboxylic acid. So if you hold this chloride ion right here, right next to the carboxylic acid, and then have another one way out here, the acidity is going to be less than if you still had this chloride ion here, but then a chloride one step in. And then once again, if you have 2 chloride ions on the carbon connected to the carboxylic acid, it's going to be much more acidic than either of these two because you have 2 chloride ions right next to the carboxylic acid instead of one here and then one here, or one here and one on this carbon that's as far away as possible from the carboxylic acid. This ties together how the larger the number of electronegative substituents and their proximity to the carboxylic acid contributes to the acidity of the molecule.
And here's a summary about the 3 different things that affect relative acidity.
Here is our contribution sheet.